Hi everyone, myself Dr. K.S.Rangasamy, Professor and Head, Department of Mathematics, K.S.Rangasamy College of Technology, Tiruchendur. In this video, let us see the subject numerical methods. In that subject, let us see how to find the solution of an equations. Let us see what do you mean by an equation. An equation is nothing but a relation between variables. Now here let us see what do you mean by system of equations. A system of equation is nothing but a set of equations which has more than one variable and one equations. To solve a system of equations, there are so many methods available, but we are going to see only two methods. One is direct method and another is indirect method. In direct methods, let us see two things. One is Gauss-Elimination method and another is Gauss-Jordan method. In indirect method, let us see Gauss-Jacobi method and Gauss-Seidel method. These are all different types of methods using to find the solution of a system of equations. Now let us see Gauss-Elimination method, how we can apply for a system of equation. First of all, let us see a system of equation. A1x plus b1y plus c1z equal d1, a2x plus b2y plus c2z equal d3, d2, a3x plus b3y plus c3z equal to d3. Here we can say it is a system of equation having three equations and variables x, y, z. Here a1, a2, a3 are coefficients of x, b1, b2, b3 are coefficients of y, c1, c2, c3 are coefficient of z. d1, d2, d3 are nothing but constants given in the right hand side of each equations. Now to follow Gauss-Elimination method, let us write this system of equation as an augmented matrix. We all of you know equation can be written as a matrix and a matrix can be rewritten as an equation. Here we are going to write it as an augmented matrix. Let us see what you mean by augmented matrix. Augmented matrix is nothing but you can write the coefficient matrix of x, y, z coefficient values, and in that rightmost column you have to include d1, d2, d3 coefficients. Now when you write the augmented matrix, we have to convert this augmented matrix as an upper triangular matrix by using row operations. And finally, if we obtain that upper triangular matrix, we can get the solution by back substitution method. Now let us see how we can apply this method, Gauss-Elimination method, to find the solution with an example. Now let us take three equations, x plus 2y plus z equal to 4, 3x minus y plus 2z equal to minus 3, x plus 2y plus 4z equal to 7. I am going to explain how to find the solution of this set of equations by using Gauss-Elimination method. As I said earlier, we have to write the first step, augmented matrix. Now what do you mean by augmented matrix? You have to write the coefficient of x, y, z in that coefficient matrix, and the rightmost constants we have to write it in that each row. Now here the first equation is x plus 2y plus z, so I have to write x coefficient as 1 and y coefficient as 2 and z coefficient as 1. Then this constant 4 I have to write here. Then in the second equation, x coefficient as 3, y coefficient as minus 1, then z coefficient as 2, and that last constant I have to write minus 3 as it is. If it is plus, you have to write plus. If it is minus, you have to take it as minus. No need to change the sign. Then third equation as it is, x plus 2y plus 4z equal to 3. Now we can say this is said to be augmented matrix with the coefficients, and the rightmost column have the constants d1, d2, d3. Then now I am going to convert this as an upper triangular matrix. How we can make it as an upper triangular matrix is by taking the pivot element and we have to make it as a 0, 0. Here let us see what is meant by pivot element. Here in the first row, first element is said to be the pivot element. Here 1 is the pivot element. Therefore, I can take it as a pivot element. And with the help of this pivot element, I have to make these two entry as 0. So suppose if the pivot element is 0, I have to rearrange the rows and I can make it as a non-zero. So that we can take the first row, first element is always non-zero. Since it is non-zero, I can keep the row as it is, and by considering this one as a pivot element, I can do this row operation and I have to make this as a 0. Therefore, I can do the operation as R2 implies R2 minus 3R1. Since it is 3 here and here it is 1, I can multiply this second row. I can keep the second row as it is, 3 minus 1, 2 minus 3, that is R2 minus 3R1. R1 is multiplied by 3, so I can subtract and I make this entry as a 0. So I have to take it as 3 minus 3, it is 0, minus 1 minus 6, it is minus 7, 2 minus 3, it is nothing but minus 1. Then similarly minus 3 minus 12, it becomes minus 15. In the same manner, now I concentrate the third row. Here it is 1, the pivot element also 1. So I can make it as direct subtraction 1 minus R3 minus R1. That is this substitution R3 minus R1. So I can make this as a 0 easily. That is 1 minus 1, it becomes 0. 2 minus 2, it becomes 0. 4 minus 1, it becomes 3. 7 minus 4, it becomes 3. So now these are all the diagonal elements. Below the diagonal elements, all the entries are 0. So I can say it is an upper triangular matrix. It is an upper triangular matrix. Since it is an upper triangular matrix, I can say that I have to find the solution with the help of back substitution. Now I can do the back substitution. That is 0x. I can rewrite this matrix as an equation. So I can write 0x plus 0y plus 3z equal to 3. If I solve, I will get z equal to 1. Similar manner, 0x minus 7y minus z equal to minus 15. If I substituted z value here, then I will get y value as 2. In the same manner, I can rewrite this as an equation x plus 2y plus z equal to 4. Then I can resubstitute all these things. Then I will get the value of z as 1. So, these are all the solution of the equation. Given equation as x equal to minus 1, y equal to z equal to 1. If we substituted these three values in any of these equations or all the equations, it will be satisfies the equation. That gives the solution of the system of equation. Therefore, it is a simpler method to find the solution of system of equation. This Gauss elimination method is a simpler method. Now with the help of this Gauss elimination method, let us go for another method, advanced method, Gauss-Jordan method. Now Gauss-Jordan method is once again a method to use to find the solution of system of equations. And that is only the basic steps we have to follow as Gauss elimination method. Then advanced 2 steps are there in Gauss-Jordan method. Now I will explain with an example. Here also I can consider same problem. I'll take the same example what you studied in that Gauss elimination method. So up to upper triangular we did in that Gauss elimination. The same procedure also we have to follow in Gauss-Jordan also. After making it as an upper triangular, the extra thing you have to follow is you have to make it as a lower triangular. What do you mean by lower triangular? Lower triangular is nothing but the entries above the diagonal should be 0. All the entries above the diagonal should be 0. If it is like that, we can say it is a lower triangular. If a matrix is upper triangular as well as lower triangular, then it is said to be diagonal matrix. From the diagonal matrix, by a direct calculation, we will get the solution of the given system of equation. This is the procedure we can follow for Gauss-Jordan method. So Gauss-Jordan method is some advanced level of Gauss elimination. In Gauss elimination, we are doing upper triangular. In Gauss elimination, we are doing both the things, upper triangular as well as lower triangular. Now, in the previous problem, we done up to upper triangular. Now, I am going to make it as lower triangular. By keeping this as a previous step, I am going to make it as lower triangular. Now, I have to use take it as last row as it is, that is 0, 0, 3, 3 as it is. Then I am going to take this as the pivot element. Third row, third element as a pivot element. With the help of this pivot element, I have to make these two as 0. So I have to use that row operation as R2 implies 3R2 plus R3, because here it is 3, here it is minus 1. Therefore, I can use opposite sign 3R2 plus R3. Therefore, now I am going to make it as a lower triangular by keeping the pivot element 3 as the pivot element, last row, third element. So I have to make the operation as 3R2 plus R3. 3R2 plus R3. I can use this operation to make this as minus 1 as 0. Since it is opposite sign, I can use addition. If it is same sign, I can use subtraction. That is the thing you have to follow. By keeping this operation as the thing, I can make this minus 1 as 0 and remaining everything I did the addition and simplify. I will get 0 minus 21, 0 minus 42. Similarly, by keeping 3 as a pivot element, here it is 1, I have to make this as a 0. So I have to multiply this R1 by 3, then direct subtraction it becomes 0. So the operation is 3R1, this is 3R1 minus R3. Therefore, I can make this operation and I have to write the value as, it becomes 3R1 is 0, it becomes that is 3 into R1 3 minus 0 it is 3, then same manner this thing and same manner this thing, I will get these values 3, 6, 0, 9. Therefore, these two operations I have to handle to make these two elements as a 0. Now you see, here it is nothing but upper triangular because all the entries below the diagonal are 0 and above this diagonal these two entries becomes 0. Now our aim is to make this element as 0 by keeping this as a pivot. Now here it is minus 21 and here it is 6. Now I am going to use that operation. Here it is, once again, here it is 6 and here it is minus 21. I have to cross multiply this by 21 and this by 6 and I have to add and I have to make it as a diagonal matrix. If I done like that, the matrix becomes like this. So now you see it is a diagonal matrix. Why I am saying it is a diagonal matrix? All the entries in the diagonal are non-zero, remaining entries are zeros. So directly I can get the value of all the variables because I can equate 63x equal to minus 63, therefore x becomes minus 1. Minus 21 y equal to minus 42, so y becomes 2, 3 z equal to 3, therefore z equal to 1. The same value which you got from that Gauss elimination. So what about the conclusion is, if you do it by Gauss-Jordan or if you do it by Gauss elimination, any method we will get the solution as same solution for the same problem. Therefore these are the direct methods we have seen in that to find the solution of system of equation. One is Gauss elimination and another is Gauss-Jordan. Now I am going to tell about that another thing, how to find the solution of a system of equation by indirect method. That is, indirect method is we have to assume something and we have to arrive the solution. Now let us see two methods are there. One is Gauss-Jacobi, another is Gauss-Seidel. Now let us see Gauss-Jacobi. Now I am going to give the rules what you have to follow for Gauss-Jacobi. The first thing you have to identify or you have to check is whether the system is diagonal dominant. Now when you can say that system is diagonally dominant is if in the first equation, if the coefficient of x should be greater than or equal to sum of the coefficient of y and z, then in the second equation, the coefficient of y should be greater than or equal to sum of the coefficient of x and z. Then in the third equation, the coefficient of z should be greater than or equal to sum of the coefficient of x and y. If this thing happen, then we can say the system is diagonally dominant. If it is diagonally dominant, then we can assume something and we can follow that Gauss-Jacobi method. If it is diagonally dominant, we have to rewrite the equations by eliminating xyz from the given equation. How to rewrite the equation? Let us see. Now, from the given set of equation, I'm going to rewrite that. I have written that rewritten equation. From the first equation, I keep x as it is, and I have to bring all the terms to other side. Therefore, this becomes d1 minus b1y minus c1 adjective divided by a1. From that second equation, I have to eliminate y, so it becomes d2 minus a2x minus c2z divided by b2. From the third equation, I can rewritten as z equal to d3 minus a3x minus b3y divided by c3. Now this is nothing but rewriting the given equation by eliminating xyz from the set of given equations. After rewritten everything, now I am going to do some initial approximation. That is, we are assuming something, that is initial approximation of x, initial approximation of y, and initial approximation of z as 0. Now with the help of this initial approximation, I have to go for first approximation. When I'm doing calculation for first approximation, I have to use that initial approximation values as it is. Since the first approximation gives d1 minus b1 into y of initial approximation minus c1 into z of initial approximation. In the same case, first approximation y gives d2 minus a2 x initial approximation minus c2 z 0 initial approximation. Same manner for z also. Now, we have to continue this process until the successive approximation has the same value. Now, with the help of this initial approximation assumed value, now I will get first approximation of the xyz. After getting the first approximation of xyz, I can go for second approximation and then third approximation and so on until the successive approximation has the same value. Let us explain with an example. Now, let us see one example. Here I will take once again a set of equations, and now I am going to solve it by Gauss-Jacobi method. Now I am going to say, first of all, I have to proceed the Gauss-Jacobi whether the system is diagonally dominant or not. Now I can say directly the system is diagonally dominant or not, because here you see this x coefficient 10 is less than or equal to sum of these two things. Similarly, in that second equation, it should be y coefficient must be greater than or equal to sum of that remaining, but it is not like that. So what I have to do is I have to rearrange the equations. How I can rearrange the equation? Since here it is coefficient of z is highest, I have to set this equation as a third equation and I have to set this equation as a second equation. If I did like that, then the system of equation is diagonally dominant, because first equation x coefficient should be greater than or equal to sum of remaining two. In the second equation, y coefficient should be greater than or equal to sum of others. In the third equation, z coefficient should be greater than or equal to sum of others. So I have to rewrite the equation as this is first and this is second and this is third equation. When I did like that, now the system becomes diagonally dominant. After interchanging the equations, it becomes diagonal dominant. Now after that, I have to go for elimination. What do you mean by elimination? From the first equation, I have to write x value in terms of others. From the second equation, I have to write y value in terms of others. From the third equation, I can write z in terms of others. If I did, I will get x equal to 3 plus 5y plus 2z divided by 10 and y equal to 3 plus 4x plus 3z divided by 10 and z equal to minus 3 minus x minus 6y divided by 10. These are all the elimination of the equations from that thing. After assuming that initial approximation as 0, I can calculate the values of initial approximation x value, y value with this assumption. Now after getting these values, I can go for first approximation as x1, y1, z1. When I go for first approximation, wherever x comes, I can replace 0.3 and y 0.3 and z is minus 0.3. With the help of these basic values, I can get the value of first approximation. Similarly, in the same manner, I can go for second approximation with these set of values. In the same manner, I may continue and I will stop the process if the consecutive approximation has the same value. Here you see 0.342, here also 0.342, here it is 0.285, here also 0.285, here it is minus 0.505, here is also minus 0.505. So I can stop the process and I can say this is the solution of the given set of equations. It is an approximate solution of the given set of equations. Then one more thing, when you do for calculation, you have to set as a 3 decimal places. You can fix the decimal places as 3. So I can get the value of x as 0.342, y as 0.285, z as minus 0.505. Then you can check whether your answer is correct or not. You can resubstitute in the given set of equations. It must be satisfied in all the 3 equations. Then you can make sure that the solution is correct. Now this thing is the method you can follow in Gauss-Jacobi method. Now I am going to explain about the Gauss-Seidel method. The Gauss-Seidel method is somewhat advanced of Gauss-Jacobi. Same thing we have to follow. Once again, diagonal dominant you have to check. After diagonal dominant you have to eliminate the equations. After eliminating, now I am going to explain with the after eliminating we have to follow some assumptions, initial assumptions. Then after that we have to follow as you did in Gauss-Jacobi. I'll explain through an example. Here I will consider one example: 10x minus 5y minus 2z equal to 3, x plus 6y plus 10z equal to minus 3, 4x minus 10y plus 3z equal to minus 3 by using Gauss-Seidel method. Now I am going to check diagonal dominant. You see what is diagonal dominant? First equation, x coefficient should be greater than or equal to sum of these two things. In second equation, y coefficient must be greater than or equal to sum of these two things. It is not like that, therefore I have to interchange the equation. Here I have to take this first equation as it is, and here I have to interchange this third equation as a second, and this third equation as a second equation as third. After interchanging, I may make sure that the coefficient of x and coefficient of y and coefficient of z are greater than or equal to sum of the remaining coefficients. So after verifying diagonal dominant, I have to eliminate the values of x, y, z from the equations. So from the first equation I can eliminate x. It becomes 1 by 10 into 3 plus 5y plus 2z. Then from the third equation, after eliminating y and simplifying with minus sign, I may get this 3 plus 4x plus 3z divided by 10. From the third equation, z may be from this equation. I may get that z equal to like this. Now with this, I am going to do some assumption. The assumption is I have to make the initial assumption as y power 0 and z power 0 as 0. This is the one thing different from the Gauss-Jacobi method. So initial approximation I can make it as y power 0 and z power 0 as 0. Now if I did y power 0 and z power 0 as 0, if I taken that thing as 0 and I can calculate x as 0.3. If I calculated x as 0.3, then as it is I have to make it into use for calculation of y. When I got x as 0.3 as an initial first approximation, I am going to make use this value in the first approximation of y. So when I use x value as 0.3 wherever, and I will get y as this. After getting the value of y, I can make use for z also. So in finding the z value, I can use x value as well as y value, new value here. So I get z as this. This is first approximation. With the help of this set of values, I can move for second approximation. Now I can use this new y value and z value when I calculate for x. After getting x, second approximation of x, I can make use of this x value for y. Similar manner, I can use it for z. These two new set of values. So when I did like this, I may arrive the solution in the sixth approximation itself as 0.34 to 0.285 minus 0.505. But we have to notice one thing: by Gauss-Seidel method is most fast convergence than Gauss-Jacobi, because in Gauss-Jacobi we may arrive the same solution Once again, usually here we arrived the same set of solution in that ninth approximation, but in Gauss-Seidel we arrived the same set of solution in the sixth approximation itself. So we can conclude that Gauss-Seidel method is faster convergence than Gauss-Jacobi method. So we arrived the solution. Okay. Thank you.